Hello, this is the technical presentation for the NASA 2019 Virtual Robotic Mining Competition. We are presenting on behalf of New York University Tannen School of Engineering, the robotic design team. My name is Theodore Kim. I am the student lead.
Hi, I'm Lucia Jesus, and I'm a junior member.
And this is our presentation. So let's first talk about system performance goals. So these goals are derived from our past experience with the competition, as well as the constraints of the competition, and our goals from other teams' performance and what we want our robot to achieve relative to that, what we think will actually win the competition. We have a lot of multiple tiers of performance goals, both for the system and subsystems and components, individual components, but these are the main 9 performance goals from which the rest were derived. They include achieving at least level 3 autonomy, maintaining within the competition parameters and constraints, utilizing minimal electrical power between 30 and 40 watt hours, minimizing mass between 60 and 70 kilograms, excavating between 1 to 5 kilograms of gravel, and reaching the desired depth to actually get the gravel from beneath the regolith as well. So moving past these performance goals, we reach the system design process. So the first step in the system design process is actually defining a philosophy by which to design the rover. So you can see this picture on the right is actually Orbit 1, last year's rover. And by the way, Orbit 2 is this year's rover's system's name, and Orbit stands for Operational Robot Built in Tandem. It's a acronym. So this is Orbit 1, this is last year's rover, and it performed extraordinarily really well. It dug, it moved, it traversed the obstacle field, but right before it was about to deposit its collected regolith, that bearing pops out in that picture. We were unable to achieve the project goal. Given that horrible event, we kind of created these 3 design principles from which to guide our ideation process. So those, number 1 is reliability, and supporting that is minimalism and parallelism. So reliability, what does it mean? Well, you don't have AAA on Mars, so the rover needs to operate and operate well. It cannot or should minimize the amount of error that it sustains. And if it does encounter a fault condition, how can it recover out of it? So that involves building the system with a sufficient margin of error, as well as creating a concept of operations that includes these error recovery states and transitions. Next is parallelism. A lot of time is wasted transitioning between states, digging to deposition, locomotion to digging, etc., etc. So how can we make the system more efficient? We'll have multiple functions occur simultaneously. That's parallelism, the idea of parallelism. So we thought that was really important, and that's a good way to minimize the little time we have, the 10 minutes we have to dig, to be able to get as many runs back and forth as possible and collect as much as possible. And then finally, minimalism. Digging is important, but a big aspect of the scoring system is deductions due to weight, bandwidth, and power consumption. So we want to minimize those. So we want to design a robot to use the minimal amount of resources, and we also want to design our concept of operations to minimize those resources as well.
So building off on the design philosophy, the team used alternative analysis to evaluate each of the design concepts of the 4 subsystems. If you see on the right of the slide, there's 4 subsystems: locomotion, deposition, storage, and digging. And underneath are each of the priorities and functions of the subsystems. So first off, the team utilized a 4-tiered process to minimize time and money spent on actually designing and testing the concepts. We first started off by pointing out and declaring our priorities for the subsystem. So our criteria specification includes what we want our robot to do and how well it will perform. Afterwards, we conducted an open ideation meeting, which everybody from our team engaged with each other to discuss different design concepts that they wanted to use for the subsystem, and we did this without regard to the criteria specification, in order just to allow creative juices to flow and a lot of different designs to be implemented. Afterwards, we conducted theoretical analysis, which is basically hardcore research on each of the design concepts that we came up with in the open ideation process. and we wanted to see which design idea was best fit for that subsystem. Afterwards, we did practical analysis, which is basically prototyping the few that were left over from theoretical analysis to see which one actually was best fit for the system. So for the digging system, we tested the conveyor belt digger, the auger, and the digging wheel. Out of those three, we chose the digging wheel because of prior experience, low power consumption. It is more complex, however, because of our prior experience, we were able to overcome those obstacles. And last but not least, it's very reliable. Afterwards, for the locomotion subsystem, we tested two prototypes, the rocker bogie and the static frame. We went with the static frame because it's a continuous frame and it offers reliable mounting points as well as a structure,
structural integrity.
Integrity, sorry.
Yes.
It also has a low mass and a low complex build. However, it doesn't offer any suspension because it is a static frame, so the risk of collision with field obstacles is high. However, to mitigate that, we chose to increase our wheel diameter to go over any bumps in the arena. For the deposition subsystem, we tested three prototypes, the expanding bin, the chute, and the tipping. We went with the tipping because it's the most simple system out of the three. It requires little energy. However, it's not as good at keeping the dust to a minimum because it is an open system. However, to avoid any problems with the system breaking because of the dust, we made sure that a filtration system was implemented into our storage. And finally, last but not least, the storage and differentiation system. We tested a vibrating sieve and a tiered inclined plane system. We decided to go with the tiered inclined plane system because of its greater inflow rate from digging and its little to no power consumption. And for the completed system, the team kind of went back and forth between using one robot or a 1.5 robot system. The one robot system would consist of just one rover responsible for depositing and digging, as well as moving. But to increase time efficiency, the 1.5 robot is a dual robot system so that one robot is purely for locomotion, moving, and deposition, while the other one is just for digging. So while the digging drum is digging, the other robot is depositing its gravel into the collection bin.
So we've passed the preliminary design phase. We have these concepts that we're going to bring forward into the actual implementation system. So how do we do it? Well, you can tell we do it very safely. One of our members is wearing goggles and gloves while he attacks another member with a mallet. Just kidding, doesn't actually happen in real life, but we are safe while doing it. I want to emphasize that. So we have 4 real stages of our implementation and methodology, and those are derived from the system engineering process which our team implemented. Number 1, preliminary design. We conducted an alternatives analysis based upon requirements and performance goals that we defined earlier on. Then we moved into final design, where we took those concepts and fleshed them out. That means CAD, that means state models, that means schematics. And high fidelity prototype. Then we moved on to fabrication. We did a variety of machining methods, both manual and automatic, computer aided. And then we chose the components. Some components are reused from previous years, so we refurbished them. And we tested each component to make sure that each thing worked individually. Then we integrated the system into its individual subsystems, and then it's the larger system. We tested each thing along the way to make sure they met the various requirements set forth for that level of complexity. Then we tested the full system in simulated competition environment and conditions, and which we'll talk about later. This is kind of a summary of the final design phase. These are the CAD models. I just want to point out, we keep saying this word tiered inclined plane, and unfortunately that's not something that we can demonstrate. So I just want to quickly point out how it works. And that's the image all the way to the right. The regolith enters from the top, the mixture. because there are several layers of ramps, inclined planes. The first one is a sieve. The kind of momentum of the fluidic regolith allows the regolith to fall through that sieve and exit through the rear, while the gravel kind of just rolls down to the bottom. Another change that we did during the final design phase was actually change the deposition mechanism from tipping to a pushing mechanism. That's because the tipping mechanism just did not dimensionally fit with the second rover. It was just too complex, and in order to maintain our design philosophy of reliability and parallelism, we changed the deposition mechanism. And then, this is an example of our fabrication. We use a combination of CNC automatic milling and hand machining. And then our integration of the final subsystem and system was mainly manual assembly.
So to verify and validate the whole system, the team took certain steps to ensure that each component adhered to its functional goal. To verify the system's mass, we individually measured each component. So it measured out to be 69 kilograms. To test out the autonomy of the system, we did this through computed models, and then afterwards we ran it through simulated errors to test how well it came back from those errors. To verify the system's ability to deposit at least 1 kilogram of gravel, we tested each component that would be responsible for collecting that gravel. So like the digging wheel, how well would it dig, how well would it hold the gravel, and and how well it can measure how much gravel is in the storage bin. And last but not least, to verify the system's ability to perform multiple tasks simultaneously, we just performed the task separately first, and then after it did it well, we did it together as a whole system. To validate the completed system, we tested it at a beach because we did not have the facilities to make a competition arena in our school. So we went to the beach and tested it there. Sand shares many similar qualities to regolith, so we decided to dig up some sand and put some gravel at a required depth to see how well the robot dug. And this testing actually occurred several times throughout the month of April to ensure that the system fulfilled all of the technical requirements it had to for the competition. System innovation. So NYU has been doing this competition for 7 years, so we've obviously learned a couple of things along the way. Our first robot in 2013 was Atlas 2, and as you see, it's a very basic design. It features a large central digging wheel on an articulating arm that collects the gravel and then deposits it into the collection bin. It was successful, however, it wasn't successful in the means that it didn't achieve minimal power consumption and mass. Afterwards, in 2017, we really wanted to achieve that minimal mass and power consumption, so that's what we kind of focused on, as you see in this design. However, however, it didn't excavate much gravel because of the torque and mechanical failure. However, the team's creativity was really illuminated by the wheels. It wasn't only made to drive, it was also made to dig because of the shovels. So if you look at Orbit 1, it's kind of like the love child between the two robots. It features the same central digging wheel as Atlas 2, as well as the same conveyor belt as Atlas 7. However, this robot is now able to, it has the capability of lowering to at least 0.65 meters below the surface to get an even deeper excavation. It was, as Teddy said before in the slide, it was great up until the mechanical failure and deposition. So this year's robot, Orbit 2, is basically the same design concept as Orbit 1. However, now it's a dual rover system to increase time efficiency. And instead of the conveyor belt system for deposition, we're now using a tipping bin.
So finally, project management. How do we put the entire thing together? The human resources aspect. So this is a basic timeline. We followed the system engineering process. We had several reviews along the way to judge in front of an independent panel of professors and industry individuals and alumni of the team to kind of show the development, to measure the development and maturity of the project along the way. Yes. This is our team structure. We implemented a matrix structure in which we had individuals from the various engineering disciplines working together on the same subsystem so that we had a really, truly interdisciplinary development of the rover. And then budget management. As you can tell by the line graph for total spending, we actually achieved almost close to linear project spending, which is nowhere close to the exponential project spending trend of death that most project managers have nightmares about. We spent money pretty consistent with our budget, our initial budget for the made in the beginning of the year. Yeah, and we got most of our funding from NYU, the various departments with NYU. Important to call that out. The hand that feeds us. Okay, so next, the demonstration. So we're gonna move aside. I'm gonna grab my PPE. I'm gonna put on my goggles. I'm gonna have three camera's gonna move now. I'm gonna have three new members on our team helping. Michael Linares, Kirsten Page, and Gian Fairchild. So we're going to be paying careful attention to safety. We're going to be calling out all of our intentions, only going to be approaching the rover when it's powered down. We also have Dan Schaffman operating the operator console over there. And he also will be communicating. We have multiple ways of e-stopping the rover. We have 2 e-stop switches for redundancy, as well as a software e-stop in case of disconnection or error for remote shutdown. I'm wearing goggles. We're all wearing goggles. Gian and Michael will be handling the rover, hence they're also wearing gloves, also correct closed-toed shoes. No sandals here. And Michael also is carrying the stick. Speak softly, carry a big stick. No, this is to turn off the rover in case of an error. From afar, we don't have to approach it too closely. We're not allowed to mark the floors, so there are no markings of the clear area, clear zone. However, each square is a foot, so we can judge how far we need to step back from that as well. So now, we're going to first demonstrate locomotion. By the way that our rover is set up, we actually cannot prop it up on anything. It's impossible. We did receive permission to run on this floor, so we will take an extra clear zone while it is running, driving briefly, to ensure that we don't, have our toes run over or anything. So yeah, let's start the demonstration. I'm going to step aside and narrate it.
All right, I'm going to turn on the robot. Turning robot on. Robot is on. Clear.
Okay, so now we're going to remove the rover. This is actually in the backwards direction first for about 1 second. So whenever you're ready, Dan.
Moving robot in 3, 2, 1.
So that's the rover. It's a little bumpy just because of the, thank you, Michael, for the catch there, because of the cleats on the wheels. Okay.
All right, I'm going to turn off the robot.
Safe to approach.
All right, turning off the robot. Robot
Okay.
off.
So now the rover's off. We're going to actually pan here to our digging rover. Again, we have Gian and Michael going to be operating it. I just want to point out a couple things. This is not attached, but we have many means of feedback on the rover, such as the linear potentiometer, which is measuring drum height. We have a weight sensor inside, as well as an infrared sensor to measure the volume of the regolith collected, as well as limit switches up the wazoo. Okay, so we're going to now run the drum.
Okay, I'm going to turn on the digging robot. Turning on the digging robot. The digging robot is on. Clear.
Clear?
Running drums in 3, 2, 1.
So the drums, the shovels will rotate around it in order to dig. Now we're going to show how it lowers down into the surface as it digs.
Engaging linear actuators in 3, 2, 1.
So ideally that would lower as it digs to get deeper into the surface. And then when it's done, it's going to raise back up.
Engaging linear actuators in 3, 2, 1.
Okay, bring it up slowly. It's doing this autonomously, so it's learned not to mess around waiting for the limit switches. Okay, so we're ready to turn off the rover.
Can I turn off the digging rover?
Safe to approach.
Turning off the digging robot. Digging robot is off.
Okay, so now I'm going to have Michael and Gian. We're going to demonstrate now the engagement of the two rovers together. The rover only weighs about 38 kilograms, hence why we only have two individuals that are. Can we make sure the wire? You don't have to. That's why we only have two people carrying it. It is a bit human intensive to put it in, but they do not come back together automatically. They never come back together once the robot is operational. Can we fix the wire, Michael? Thank you. Okay. So when to engage, the linear actuator will go down, and these forks will rest on this lift here, and it will be lifted up off of the ground. Okay. Let's do that.
Can I turn the robot on?
Safe to approach.
Robot is on.
Clear.
Clear.
Clear. So now he will bring the linear actuators down and lift the robot off of the ground. Go ahead. Yeah,
Engaging linear actuators in 3, 2, 1.
All right. So we can get the camera underneath so we can see that it's off the ground there. Yep. Don't go too close. It's still on. Okay. Still within the clear zone. It's off the ground. And in this configuration that the rover will drive from the starting position to the mining area. Okay, thank you. Now we're going to disengage the rover. That involves raising the linear actuators such that the rover now lays on the ground. Okay, Dan, whenever.
Engaging linear actuators in 3, 2, 1.
So, it's almost there. All right, so now it is off. Okay, we're going to turn the rover off, we're going to disengage the two rovers, and then we're going to finish up with the demonstration deposition.
I'm going to turn the robot off.
Safe to approach.
Robot is off.
Okay, so now the robot is off, we're going to pull out, Michael and Gian are going to pull out the deposition rover. Okay. So now they're disengaged and this would drive away. Finally, just to demonstrate the deposition mechanism, how it is this plate here will move up to push out the regolith and then move back down to accept more regolith. And then this entire assembly moves down to get the regolith from the drum, and then we'll move up to push it into the collection bin. Okay? So Dan, oh wait, we gotta turn it on, though.
All right, I'm going to turn on the robot.
Safe to approach.
All right, turning on the robot. Robot is on.
Clear.
Clear?
Engaging linear actuators in 3, 2, 1.
Oops. Oopsie doops.
Sorry.
False start. And that is in the collection bin, and we're assuming that there's regolith inside of the deposition mechanism now, so we're going to pull out the plunger to push all the deposition out, all of the regolith from inside the deposition mechanism out into the collection bin.
Big wrap.
Engaging motors in 3, 2, 1.
All right, and that would push out all the regolith. All right, we're going to turn off the rover.
All right, I'm going to turn off the robot.
Safe to approach.
Turning off the robot.
And then the robot is
Robot is
powered
off.
down. And that concludes the technical demonstration and presentation for the 2019 NASA Virtual Robotic Mining Competition. I know we ran a little long, sorry about that. And yes, thank you for joining us. We've been at NYU Cannon School of Engineering. Thank you.